All right, so first of all, a lot of today is going to be review because we balanced equations before. We balanced them in physical science. You probably balanced equations a little bit in biology, or at least had to read chemical equations in biology. So we've done this before, but in chemistry, we're gonna take it one step further. But before we do that, we just have to review everything. So first of all, chemical reactions have two parts. We have the reactants, which are the substances you start with, and we have the products, which are the substances you end up with. The reactants will always turn into the products, and we separate them with an arrow. Okay, the arrow always points in the direction of the product. Okay, again, this is straight from physical science, correct? So for example, if I'm making chocolate chip cookies, I'm going to take flour and sugar and vanilla and chocolate chips, and I'm sure there's a few baking soda, baking powder, whatever. You put them all in there, you mix them in a bowl, you spoon them out on a cookie sheet, and you set them on the stove. That's not going to work, right? You actually have to put it in the oven, right? And then, because you're adding heat, you're going to eventually get cookies, right? A chemical reaction is taking place. It's pointing towards the cookies. Am I going to get my reactants back very easily? No. So here's another example. This person's baking bread. You mix all of these things together, you put them in the oven, and you get your product of bread. All right, so atoms are not created or destroyed. This is the law of conservation of mass. You start with one hydrogen, you end with one hydrogen. You start with one sodium, you end with one sodium, etc. But we can describe these reactions in several ways. One of them you've used before. The other three you've probably never, well, you've done two of these before. The other two you've probably never done before. The first one is in a sentence. Every single item is a word. So if I say copper reacts with chlorine to form copper to chloride. Honestly, this is like a math word problem. It's giving you a lot of information, and it's can we translate it into a chemical formula? Okay. The second way is using a word equation. It's telling you the exact same thing as a sentence, except it is substituting in pluses and arrows for the signal words. So copper reacting with chlorine, react is a signal word for they're being put in the same container. They're being added together, however you want to look at it. We're substituting to form with the arrow. The arrow can mean to form or yield or create or react with. There's lots of different words for that. And then it's going to form copper to chloride. So basically we took out all the signal words and we put in our math symbols. Speaking of symbols, there are lots of symbols in chemical equations, and we know some of them, but we don't know all of them. The first one is the arrow. We've used these before in physical science. The arrow separates the reactants from the products, and it always points towards the products. So we can read it as reacting to form, or yielding, or creating, or reacting with, or forming. I mean, there's lots and lots and lots of different signal words that you need to draw the arrow. The plus sign can read as and. So copper plus oxygen, or copper and oxygen, or copper with oxygen. There's lots of different ways to read the plus sign, but basically you're meaning you're adding them together. And then the next three, everyone has seen before. Solid, liquid, gas. Okay, we put a little s after the formula to say that it's solid. We put a little g after something to make it a gas. And we put a little L after something to show you that it is a liquid. Now, when we first start off writing chemical equations, these are not important because they're not going to play a factor, but what state of matter something is in is very important. Like, for instance, let's talk about mercury. What state of matter is mercury usually in? Liquid. Is mercury good for you?
No.
No, but up until the 1980s, maybe even the early 1990s, they used mercury to fill cavities in your mouth. So if mercury is so bad for you, then why would we put it in our mouth, right? Well, you think solid mercury is not so bad. Liquid mercury, honestly, is not that bad either. It's the gas form of mercury. Mercury can, if you were to spill mercury, like if you break a thermometer or something with mercury in it, it separates really easily and it will evaporate really quickly into the gas form. It's the gas form that is bad for you. So in a chemical reaction, if we're producing solid mercury, is that okay? Yeah. It's when we're producing vapor. It's when we're producing the gas form of mercury that it's bad. So are the states of matter super important? Not necessarily, but it is important when you're trying to figure out what reactants are, what the products are, and sometimes you won't even get a reaction. Sometimes a reaction will only take place if you're dealing with the liquid version of something, but if you have the solid version, it won't work. So they're not super important, but as we get more and more in depth in this, they'll become a little more important. Okay, the next couple of symbols you may or may not have used before. The first one is aqueous. I believe in physical science we kind of taught you what aqueous was, but we didn't necessarily make you use it. We just let you call everything a liquid. Aqueous means that it is dissolved in water, and we use a AQ after the chemical formula. And an example of this would be salt water. If I put salt in water, is it still salt? Is it still water? Yes, nothing changed. Is the salt technically a liquid? No. Okay, but do you think it's going to be easy to do a chemical reaction with a salt if I just pour it out of the container? No. Is salt going to conduct electricity if you just pour it straight out of the container? No, but if I dissolve it into water, is it going to conduct electricity? Yes, but did I change the chemical properties of it? No. So another way to denote it is we would put sodium chloride, AQ, telling you that the only way this reaction is going to take place is if you dissolve it into water, but water itself is not doing anything in the reaction. It's just kind of like holding the place. It's giving the reaction a way to happen, but it's not really part of the chemical reaction. So, yes, salt water is a liquid, but the water has nothing to do with it, but the salt is what's doing the reacting. So it's just a different way to denote something. The next one is an arrow pointing up. This is used after a product to indicate that a gas has been produced. So for instance, if I'm taking hydrochloric acid and I'm mixing it with magnesium, okay, hydrogen gas is going to be produced. Well, it started off as a liquid. Now it is in the gas form. So we could write G after it, or another way that you're going to see it is writing the arrow up. I prefer writing the G after it. That's how I write it. That's how most of you choose to write it, but you might also see this in textbooks or in your tests and so on and so forth, just to make sure that you know what it means. And the arrow in the opposite direction, pointing down, is used after a product to indicate that it is a solid that is being produced. So I believe next week when we do our lab, we're going to mix two liquids together and a solid will precipitate down at the bottom. We could draw an arrow after it to show that it is forming a solid from two liquids. Or you could just write S after it, whichever you prefer. I'm okay with both. Alright, the next symbol kind of looks like an equal sign, but it's really two arrows. Does everyone see the two arrows? Okay, one arrow is pointing towards the right, one arrow is pointing towards the left. Remember, the arrow points in the direction of the products, correct? So if the arrow is pointing in both directions, it means both sides can be the product, which means the reaction is reversible. So it'll form to the right just as fast as it'll form to the left. So when you're watching this reaction, it might not actually look like anything's happening because your product is being formed just as fast as it is being broken back down. All right, and this is the important part. Next week in our lab, you have to be able to not only read this, but you have to be able to write this in your chemical reactions. This looks like a triangle, right? But we know in science to read that as a delta, correct? Usually in a chemical formula, it means change in, correct? Well, in chemical reactions, it means that we are changing the chemical reaction by adding heat. So the triangle and heat mean the exact same thing. So you can write out heat, or you can write the triangle. It means the exact same thing. But this means that in order for the reaction to take place, we have to add heat. So to get my cookies to turn into cookies, I have to put them in the oven, right? Now, I could take them outside in August, and after like 6 or 7 hours, they might bake if it's hot enough, right? But if we take them outside right now, although I do think it's 40 degrees outside today, it's probably not going to happen, correct? Because we need heat to make the reaction happen. Okay, another way that we can show this is by writing an element on top of the arrow. So this time around we see the symbol PT, which is the symbol for platinum. So when you see an element written on top of it, it is telling you that it is a catalyst, which we'll talk about in just a second. But in order for this reaction to take place, we need a catalyst. Something has to be added to this reaction to get it to start. If we don't add a catalyst, this reaction will never take place. Alright, so I'm sure you're super curious what a catalyst is, right? Alright, a catalyst is a substance that speeds up a reaction, but the important part is without changing or being used up by the reaction. So, yes, in the last reaction, platinum was the catalyst, but it is not going to be a reactant and it is not going to be a product. It'll stay in the exact same form that it started in. If you start with 5 grams of platinum, you're going to end with 5 grams of platinum. It is specifically there only to speed up the reaction. Hey, can anybody think of another name for a catalyst? Bree? What's another name for a catalyst? Look at your computer. An enzyme. Okay, enzymes are biological or protein catalysts in your body. So when we're talking about catalysts inside of us speeding up our chemical reactions, they're termed enzymes, which you've probably heard in biology, correct? All right, so we've talked about writing chemical equations in like a paragraph, correct? We've talked about writing chemical equations, taking out the signal words and adding the pluses and the arrows, right? But the most important type to communicate a chemical reaction with is a skeleton equation, which is what you guys have been using in physical science and chemistry. Okay? This uses formulas and symbols to describe a reaction. However, it doesn't necessarily indicate a balanced number. So like for instance, if I wrote in the example problem we did from the simulation, we had N2 plus H2 yielding NH3, correct? This is a skeleton equation. Is this balanced? No. But it's telling you what the molecules are and who's reacting with who, correct? Right? Are we awake? Okay, so this is a skeleton equation. The thing that we've never done before is you guys have never had to write the skeleton equation before. You've always been given it and then told to balance it, correct? That's what happened in physical science. We gave you a handout. It had the equations already written and you just had to do the math to balance them. Well, in chemistry, guess what you're going to have to do? You're going to have to learn how to write them, and then you're going to have to balance them, and then you're going to have to learn how to identify them. So you're going to have to do a bigger process. Okay, but all chemical equations are just a description of the reaction. So we've been using ionic and covalent compounding rules for a month and a half now. So hopefully this process will go a little bit smoother. So let's see if we can write this. So here we have our paragraph form, right? Sentence form. Now, for those of you who have taken the ACT or an EOC, what is the most important testing strategy when you're taking a standardized test that's timed? Before you can even guess the answer. You need to read the direction, you need to read the question, and since it's timed, hopefully you should only read it once, right? The more times you read the question, the more time it takes you to answer the question, the less time you have for all your other questions. So you need to learn reading habits. So honestly, as I read this, I'm going to underline and I'm going to circle. I'm going to underline my compounds and I'm going to circle my signal words. So solid iron 3 sulfide reacts with gaseous hydrogen chloride to form iron 3 chloride and hydrogen sulfide gas. That is a paragraph. We've never done this before. You've never been asked to write a skeleton equation. So right off the bat, this honestly looks like a whole bunch of words, correct? But do I have to go back and actually reread this again? No. Now that I've read it, I start back at the beginning, and let's do one compound at a time. So solid iron, iron is Fe. What does the 3 mean? Iron 3, what's that mean? It has a charge of 3 positive. Hydrogen sulfide. The "ide" is telling you it's in a chemical compound, right? So that's how I know to stick these guys together. What's the charge of sulfur? It's in the 6th column, has 6 valence electrons. To negative, because he is most likely going to steal 2 electrons, right? So +3, -2. That doesn't look like neutral to me. What do? Cross them. So we're going to need 2 irons for every 3 sulfurs, right? Okay, it reacts with, what should I write? Reacts with plus sign. Reacts with gaseous. Oop, we forgot our solid. See, I still forget things. We forgot to say that this was a solid, right? Reacts with gaseous hydrogen chloride. Again, hydrogen. What kind of charge does hydrogen have? +1. What about chlorine? -1, and it's a gas form, so we're going to write a G. Okay, is -1 and +1 neutral? Yep. So it is going to react to form. What do I write for to form? An arrow. Hopefully I don't run out of room. Iron 3 chloride, so I'm going to do the same thing. We're going to write iron. Well, that's 3+, right? Chlorine still has the same charge of 1-. That's not neutral, is it? So how do I fix it? Cross the charges. Now everybody's happy, correct? Did it tell me my state of matter? No, but we know something about iron, don't we? What form is iron usually in? Solid. So if it doesn't tell you, make an educated guess, okay? And hydrogen, sulfide, gas. And I'm going to run out of room, so I'm going to write it down here. Hydrogen is still +1. Sulfur is still 2-. Cross them, right? So it'll be H2S, and we have the gas form. That's how you write a skeleton equation. Is this balanced? No. Well, that's okay. We can balance the equation. It's this step that usually is the hardest because you have to remember all your covalent and ionic rules. All right. So there is one more example that we're actually going to do tomorrow in the beginning of class. But let's see if we can do the opposite. Let's see if we can take a skeleton equation and write the words out. So, starting right here, how could I describe the first guy? Solid iron. How could I write the plus sign? Or what's a better way? Reacts with, right? Because these two things are reacting to form, correct? So solid iron reacts with, how should I name that guy? Oxygen gas or gaseous oxygen, right? Because oxygen is a diatomic molecule, so we don't change his name at all, do we? So it'll be how do I write the arrow? To form or yield or, there's lots of options. To form. And then how in the world are we going to denote that guy? Fe2O3. So we have an ionic compound with a transitional metal. So we're going to need to know iron 2. Is it iron 2? It's iron 3. Why is it iron 3? Because oxygen has a charge of -2, but there are 3 of them, correct? So altogether we have a charge of -6, which means we also have to have a charge of +6, but there is being split between 2 irons. So each one's going to be +3. And then oxide, we change oxygen, we change the suffix to oxide. And this is in the solid form. So again, we've never done this before. This takes some practice to be able to go back and forth because it involves so many steps, right? But this is what we're going to do all day tomorrow. All we're going to do is go back and forth between the two, okay? Right, there's another example, but we're going to do that one again tomorrow to kind of refresh our memory. But let's look at this one. Let's see if we can do this one. First off, do we have an ionic compound anymore? Nope. This is a covalent compound, right? Because it involves two nonmetals. So are we going to name it just a little bit different? Yes. So what's his name going to be? Nitrogen dioxide is going to what? Break apart, form, right? So let's say break apart. And I'm going to run out of room, of course. Is going to break apart, but looky here, what do we have here? We have a catalyst of PT. So it's going to break apart under the influence of platinum, or with the catalyst platinum, however you want to put that, to form, what's this guy called? Diatomic molecule. Or do we change the name of a diatomic molecule? No. So it's going to form nitrogen gas plus oxygen gas, correct? Diatomic molecules, we don't change their name. It's a given. If you don't have those memorized, you should probably memorize them now. All right, and then last but not least, we need to make a balanced chemical equation. Atoms cannot be created or destroyed in an ordinary reaction. We have to start and end with the exact same number. A balanced equation has the same number of each element on each side. So, let's do a few rules. There are lots of ways you can balance chemical equations. Everybody kind of comes up with their own way and you tweak it a little bit, but as long as you show some sort of work, I'm completely happy. So, rules for balancing equations. First of all, you need to assemble the correct formulas for all the reactants and products using a plus or an arrow. So this is making a skeleton equation, right? Secondly, you need to count the number of atoms of each type appearing on both sides. You need to figure out where you need to start. What's unbalanced? You only need to balance the unbalanced ones, correct? Then you need to balance the elements one at a time. I just make a list, and I start at the top and I work my way down, but I always save hydrogen and oxygen till the end because those guys often appear in more than one compound. So if you try to balance them first, it actually is much more difficult. So if you wait till the end, those actually usually balance themselves, and I actually save oxygen until the very, very last. And then the step that everybody likes to skip is double check your answers. Okay, never, ever, ever change a subscript to balance an equation. You can only change the coefficients. Again, why do we not change subscripts? Because the reason they're there is to make sure the elements are following the octet rule. If you change the subscripts, they won't be following the octet rule anymore, correct? Okay, so for instance, if we take H2O and instead of balancing it, we change it to H2O2, that's changing water into hydrogen peroxide. I don't know about you guys, but I don't want to drink hydrogen peroxide when I think I'm drinking water, right? Okay. Thirdly, or not thirdly, you should never put a coefficient in the middle of the formula. So, you can put the 2 in front of sodium chloride, but you can never put the 2 in the center. Because if you put the 2 in the center, you're honestly trying to make a subscript, and we can't do that. You can only put the number out in front. So, let's see. I think we have plenty of time for an example. Let's do an example, and let's follow these steps. So, that's not the one I want. All right, we're going to do the same example that we did in the previous slide. So let's see here. Okay, so let's go back to this first skeleton equation. We already did all of the work for this, so let's rewrite it. So we're going to have iron. So we already did all of the work for that. So let's see how well I can remember this. Somebody help me remember this, okay? Oh, it stayed. Okay, so we have this guy, so let's try to balance it. So the first step is to write the skeleton equation, which we already did, correct? The next step is to count everything. So let's change the color so we can see. What I do is underneath the arrow, I list all of my elements. So I have iron, then I have sulfur, then I have hydrogen, then I have chlorine, right? I listed all of my elements, and now I'm going to count them. On the left side, we have 2, right? So I put a 2 right here. On the left side, we have 3 sulfurs. On the left side, we have 1 hydrogen. On the left side, we have 1 chlorine. I'm just counting. I do the same thing on the right side. We have 1 iron. We have 3 chlorines. We have 2 hydrogens. And we have 1 sulfur. So this honestly just kind of gives you a place so that you know where to start. Can we do some of this in our head sometimes? Yes. But again, like I said, I really want you, I can't read your mind. I need you to write something down because balance equation is one of those things that's really easy to copy. So I need to see some sort of thought process, okay? So now let's balance this. Let's use green or purple. All right, so I can only add coefficients, right? So I honestly start at the top and work my way down. My irons are unbalanced, right? So I have 2 irons on the left. I only have 1 on the right. So to fix that problem, I put a 2 right here.
Students, could I have your attention for a moment, please? If you were nominated for Rose Royalty, Simone Time will be here tomorrow morning at 8:15 for a picture. Again, if you were on the nomination ballot for Rose Royalty, Simone Time will be taking your picture tomorrow morning at 8:15.
All right, so to fix my irons, I put a 2 in front of my iron chloride, right? And that changed my irons, but it also changed my chlorines, right? So this is one of those examples as you try to balance this, you're creating more problems along the way, right? But that's okay, I just keep going. Next, I'm going to fix sulfur. Sulfur has 3 on the left, but only 1 on the right, so I'm going to add a coefficient of 3 right here. But that doesn't just change my sulfurs, does it? It also changes my hydrogens to a 6. And I did not write a 3. There we go. Now it's a 3. Okay? But again, I fixed one problem and I created another. So now I need to balance hydrogen, but I like to save hydrogen till the end, so I'm going to skip it. I'm going to move on to chlorine, right? So I have 6 on the right now, and I only have 1 on the left, so I need to add a coefficient of 6 right here. So that changes this to a 6, but it also changes my hydrogens to a 6. So did we fix my hydrogen along the way? Yep, which is exactly why I save him till the end. So this is a pretty straightforward example. I gave you a few on your homework that are, I try not to give you too difficult of ones. I did give you one that's a little bit difficult, just depending on, because hydrogen's in more than one spot. But there are 5 examples. I really want them done before you get here tomorrow. You have 6 minutes. Plenty of time. So you can at least get 3 of them done, if not all of them. All right.